All right, so let's dive into this fascinating mission, NASA's Double Asteroid Redirection Test, or DART. To kick things off, what was the overarching goal behind this mission?
The DART mission was essentially a real-world test of planetary defense. NASA wanted to see if we could deflect an asteroid heading for Earth by deliberately crashing a spacecraft into it. The idea is to use the momentum of the spacecraft and the debris expelled from the asteroid upon impact to nudge it slightly off course, enough to avoid a potential collision with our planet.
All right, that sounds like something out of a sci-fi movie. So this wasn't about saving Earth at the moment, right? The asteroids in question, Didymos and its moon, Dimorphos, weren't threats to us?
Exactly. Neither asteroid posed a threat. Didymos is a binary asteroid system, with Dimorphos being a small moon orbiting Didymos. But this system provided a perfect testing ground because it's relatively close to Earth, and we could measure how much Dimorphos shifted in its orbit after the collision. The deflection didn't create any risk of the system becoming a hazard, either.
Got it. The mission sounds wildly ambitious. Let's break it down a bit. Tell me about the spacecraft itself and how it worked.
Sure. The DART spacecraft was a relatively small impactor, weighing about 610 kilograms. The key tool was its Draco camera, which not only helped it navigate autonomously, but also provided detailed images of Dimorphos as it zeroed in. The autonomous navigation software, SmartNav, guided DART to lock onto the asteroid and ensure a direct head-on collision. One notable part of its design was the roll-out solar array, a new type of solar panel providing significant power for its propulsion and operations.
And what about the actual collision? What happened when DART hit Dimorphos?
The spacecraft struck Dimorphos at about 6.6 kilometers per second, or roughly 22,500 kilometers per hour. The impact itself didn't just transfer momentum, it also ejected a huge plume of debris into space. This ejecta created recoil, amplifying the deflection. As a result, Dimorphos' orbital period around Didymos shortened by 32 minutes. That's a far more significant change than the team's minimum success threshold of 73 seconds.
Wait, so some of the momentum transfer came not from the impact itself, but from all that ejected debris? That's pretty wild.
It really is. They call it the momentum enhancement effect. Essentially, the debris acts like a jet of gas pushing the asteroid further than the collision alone would. The momentum transfer ended up being 3.6 times greater than if the impact had been perfectly clean, without ejecta.
That's incredible. Now, I understand there was another companion to DART, right? Something about a CubeSat?
Yes, the Italian Space Agency contributed a secondary spacecraft called Lycia Cube. It separated from DART about 15 days before the impact, and was there to capture images of the immediate aftermath. It gave us an amazing view of the ejecta plume and helped validate models of what happens during such a kinetic impact in space.
And how were we observing this collision and measuring its effects? I imagine there wasn't just one telescope involved.
Not at all. Observations were carried out from a variety of sources, including ground-based telescopes, radar systems, and even space telescopes like Hubble and James Webb. Their combined efforts made it possible to precisely measure how Dimorphos' orbit around Didymos changed over time post-impact.
This brings up an interesting point. If this worked so well, what does it mean for future planetary defense efforts? Are we saying that this approach could genuinely protect Earth from future asteroid threats?
It could. This proof-of-concept mission showed that early intervention, even with a relatively small spacecraft, can nudge an asteroid enough to avoid a disaster. But timing is critical. A slight velocity change accumulates over time and can lead to massive shifts in position over the years. For a hypothetical Earth-threatening asteroid, a similar intervention could give us the buffer needed.
But let's be honest, this has never been done before. How much confidence did this mission give scientists that we could pull off something like this if it were a real emergency?
A lot, actually, especially because DART exceeded expectations. The final results will inform strategies for future missions, helping refine models for different asteroid compositions and sizes. And it showed how international cooperation, NASA, the European Space Agency, and others, could amplify efforts in planetary defense.
Speaking of international effort, there's a follow-up mission, right? Something to study what happened in more detail?
That's right, ESA's Hera mission. Set to arrive at Didymos and Dimorphos in 2026, Hera will study the system in much greater detail to assess the full effects of the impact, including the crater left on Dimorphos and changes to its structure or composition. It's a vital step for understanding how this method could be applied to other targets in the future.
So, between DART and Hera, we're essentially building a comprehensive playbook on asteroid deflection. Before we wrap this up, what was the biggest takeaway for you from this mission?
For me, it's the unprecedented combination of precision, collaboration, and the sheer audacity of humanity to attempt something like this. It's a reassuring thought that not only are we mapping the skies for potential asteroid threats, but we also have a viable strategy to deal with them decades in advance.
That's both inspiring and humbling. Well, thanks for breaking this down. It's fascinating to think our generation might be the first with the tools to guard the planet against cosmic threats. Who knew planetary defense could be this exciting?